Hi, this is 13.3. We're dealing with the dot product. The dot product is when we take two vectors and we can do some sort of scalar product with them. And we'll look at eventually what does the dot product do for us. So the definition of the dot product for any two vectors, and you could have it in any dimensions that you want, but you're just going to take the v and w and you're going to multiply their respective components and then add them together. That's all you do. The geometric definition is more so here, where we're going to take the magnitude. If we take the dot product, v times w would be the magnitude of v and the magnitude of w, and we're going to then multiply by the cosine of theta, where theta is the angle between these two, and then we have and theta between 0 and pi. So for example, we want to go ahead and do the dot product here for v dot u, given that v is 2i plus j and u is equal to 3i minus j. So this is v dot u is equal to, I'm just going to take the 2 and multiply it by the 3, and then plus the 1 times the negative 1. So all I did was take each one of the components. Here's the 2, there's the 2, there's the 3, there's the 3, and then the 1 and the negative 1, multiply them together. And we get 5. Now, one consequence of this is that if I ever want to find the angle between two vectors, I can rewrite this geometric interpretation by solving for the cosine, which would be equal to the dot product of u dot v and then divided by each one of the respective magnitudes. So then I take the inverse cosine, make sure that it's in degree mode for most of what we're doing. That would give you your angle. So if I wanted to find the angle between these two, I can go ahead and do cosine of theta is equal to the dot product, which we did up above, which would be the 5, and then the magnitude of each one of these vectors. Well, this one would be 4 plus 1, so it would be square root of 5, and then we get the square root of 10 for each one of these respective magnitudes. So I just took 2 squared plus 1 squared and then 3 squared plus 1 squared and got each one of these respectively. So now the cosine of this thing, theta, is going to be the inverse cosine of this angle measurement. Now you got to be careful with this too, is to make sure that you get the right angle for whatever you're looking at. If it's between 0 and 90, it should be no problem. If it's greater than 90, less than 180, then we might have to do some manipulation. We'll see how that works. But if that does happen, then your cosine value would be negative, and it will tell you. And if we pop this into our calculator, we're going to get theta is equal to pi over 4. Notice this is in radians, so if you had to change it over to degrees, you would go ahead and multiply by 180 all over pi. And when you do that, you're going to get 45 degrees. Okay? So then that is how you find the angle in between the two vectors. If the vectors are in 3 space, finding the angle between is a little bit weirder, but we'll go ahead and try to find that right now. But before we do, make sure that you do note the different properties of the dot product. Just reverse the multiplications around. If I just put in a scalar, and then if I do the distributive property, I can also take care of that. And then here's one thing: two non-zero vectors are perpendicular or orthogonal if and only if the dot product is equal to 0. That would give us the cosine of theta being 0. And when does that happen? Well, that would happen at pi over 2, or 90 degrees. So that would tell us that we're 90 degrees. And then the magnitude, if we do a vector by itself, then the dot product of that is just going to give us the magnitude squared, because you're just multiplying the respective components together, which is just the same thing as square in each of the components. And then you don't take the square root in the end, so that's why this is the magnitude squared. So go ahead and try to find the angle theta in between each one of these vectors. So for example 2, I've given you some different vectors. You can go ahead and read this. And with those, with those vectors, find the angle in between the following pairs. So pause, try A, B, and C and see what happens. Okay, so we get the cosine of theta is equal to, I hope you went through and tried this yourself, negative 8 over 2 times the square root of 70, which would be negative 4 over square root of 70. If you go ahead and punch this into your calculator then, which is negative 118.561 degrees. If you did it in radians, you get 2.069. So you can just punch that in your calculator, that will give it to you. And then if you go ahead and do B, you notice that in the numerator, you're going to get 0 divided by some number. So the cosine of theta is equal to 0. When that happens, you're at 90 degrees. So what's true about U and V? Well, U is perpendicular to W. And another word that we use is that U and W are orthogonal. And that just means perpendicular. Okay, so then try this one, V and Z. And so in this case, cosine of theta is equal to negative 8 plus 0 minus 2 all over square root of 20 times square root of 5. Notice that I did these over here to simplify things for me a little bit. And then we end up with negative 10. This is a minus, by the way. Negative 10 all over square root of 100. Well, that just turns out to be negative 1. When is the cosine of theta equal to negative 1? Theta is equal to, in this case, it would be 180 degrees. If we have 180 degrees or we have 0 degrees, that means that these two angles, V and Z, are then going to be parallel. So we are parallel. Okay, and then here, this represents that last one that we did way up here. Find the dot product of U dot U. Try it. So if you do U dot U, you get 14. And then if you look at that as compared to up here, what is my magnitude of U? And then I'm going to get the square root of 14. Obviously, that's going to be the magnitude squared. So this is going to be the magnitude of U, and then I need to square this. Notice that I keep on forgetting the little arrows above my vectors. That's a no-no. Sorry about that. All of these should have them over the top too. One thing we like to look at is the spreadsheet to see where we can maybe crank some of these things out. So I programmed this spreadsheet to go ahead and do the dot product for us. And when I did that, dot product. When I did the dot product, I kind of chased my tail around. What happened is that I did a vector U, which was started in standard position. So it's just going to be 1 unit, standard position relative to the unit circle, but it's just going to be 1 unit on the x-axis, so it's just I. And then V, I did to be the other vector with some endpoint. That endpoint depending upon these different angle measurements that we do have. So I went ahead and did the geometric interpretation of this, and so I calculated the cosine of theta. When I did this, I did the U dot V all over the magnitude of U times the magnitude of V. If I put the arrows in there, it will get kind of messy, but there it is. Okay, so that's how I calculated it. Well, what happens when I have just a segment that is exactly the same? I'm going to get 0 degrees in between the two, and what's the cosine of 0? Well, that turns out to be my 1 right here. So I am kind of chasing my tail around, as I say, because I could have just taken the cosine of 0 degrees and I would have got this value. But then I didn't. So look at these. And this is theta in radians and then degrees. And so if I did 30 degrees, I calculated cosine of theta based upon this formula again, I get 0.87. If I find theta by doing the inverse cosine of that, I'm going to get 0.52 radians, which is 30 degrees, which is the angle measurement that I wanted. Now if I keep on doing this, I got to be a little bit careful, because then all of a sudden, once I get past 180, things change a little bit. Notice that my angle measurement doesn't turn out to be correct. That's why the theorem stated in between 0 and 180 for what we had. Then we'd have to subtract 360. So in other words, we're going to have these angles like this. Are you talking about theta here, or are you talking about theta here? Well, we're talking about this one in here, not this one. Okay, so that's what you just got to be careful of a little bit. Notice that the cosine comes out to be negative once you go over 90 degrees, and then you're up to 180, it would be negative for what we're dealing with. I thought it was kind of nice to see when you get your values out, just to look at what kind of angle measurements you're going to have. However, that should just be kind of your common knowledge from trig. Okay, the next theorem, the equation of a plane with a normal vector and the point containing this point is this right here. Now, I think I'm going to wait for class, so remind me in class to ask me about how do you derive this thing, because I don't want to do it right here because we've got a lot to do in this lesson. But we can go ahead and follow that up. So if we want the equation of a plane with a normal that is perpendicular to the plane, so here's a plane, and then here's my normal. Then I can take another vector, which is in the plane. I guess maybe I'm doing this now. But this would be, the point right here would be x naught, y naught, z naught. That would be this point right here, and then the tip of that point would just be some generic x, y, z. So if I want to find the vector, the red one, so if I write the equation of that vector, that red one, I'm going to get x minus x naught I plus y minus y naught j plus z minus z naught k. And then I have my normal vector, which would be given, so that's this one in purple that I've drawn here. And so what's true about two vectors that are perpendicular to each other? Well, we do know then that our dot product is going to be equal to 0. So when I do the dot product, that's really what we're doing right here. So I'm going to take the coefficient a, b, and c, and I'm going to multiply them by x minus x naught, y minus y naught, and z minus z naught. And so that's where we get our equation from. Read example number 3, and we want to write the equation of the plane perpendicular to this normal that passes through this point right here. So straight away I can find a, b, and c for my equation, and then I have my x naught, y naught, z naught, and so I can just go 1 times x minus 2 plus negative 1, y minus 3, and then plus 2, and then I have my z plus 4. That's all going to be equal to 0. There's my equation to my plane. Wow, is that easy? If you clean this up and simplify, and this would be the equation of my plane. Notice that I'd like to cross my z's just because then it doesn't look like a 2, or you loop your 2's, but I don't always do that, as you see there. And this form that we just have here is in this form here. We just solve for that d value. For part B, then, it says find a vector parallel to the plane. Well, anything that is going to be perpendicular to the normal will be a vector parallel to the plane. So if I want to find this a different way, well, what I could do is just take these values, knowing that any vector that I do pick, and I do the dot product with this, I'm going to get 0. So I know that 1 times negative, well, whatever, I'm writing this out correctly, plus 2, this will all equal 0. So pick some numbers. Well, I can plug in 5. 5, those will cancel each other out, so then I just get 0. So I can do V is equal to 5I plus 5J. I did this wrong. 5J plus 0K. That would give me my vector, or one vector that would be parallel to what we do have there, to the plane that we have there. All right, then we can also go ahead and extend the dot product into n dimensions. So we've done different product lines with prices and different things like that where we might multiply those pieces together. And then we can do this in whatever dimension that we do want for the dot product. So you just multiply the respective pieces. So if this was burgers and they cost $4, that might be one instance. If you had hot dogs and they cost $3, that would be another instance. If you had snow cones that cost $2, that could be another component or another piece of this, so on. We can get the dot product from that. I was kind of confused on this, but this is wrong. So this should be times, not a comma. Now, I didn't put a dot in there, but it is a times. Notice that they do have the arrows over U and V, but each one of the components, they don't put an arrow over the top. So really, this should read out like this. Now what we want to do is go ahead and look at what the dot product does for us, and it's called a projection. So what's going to happen is that we're going to have a vector, in this case, namely V, and what we want to do is project it onto another vector, which in this case is my U. And so when I project it, it's like a little light, little Mr. Sunshine out here. And then when I do the shadow, what does that shadow do if that shadow or that light is perpendicular to this U vector? Where will it shine? And then that would be what this book calls my V parallel. So this is probably bad, but I'm going to use this for V parallel and this for V perpendicular because I don't like writing out all that stuff. So that's what we're going to end up with. So then if I graph this one right here, this one would be my V perpendicular. So when they say that, all they're trying to do is say, okay, it's parallel to what? Well, it's parallel to U. So when they say V parallel, that's going to be parallel to whatever I'm projecting onto. And I wrote this here. Note that V parallel is just some kind of scalar of U, the U vector that I do have here. So here's V parallel. And it's just a portion of the U that I do have. Now, it might be longer than U, it might be shorter, it might be the same length, but regardless, it is going to be a scalar multiple of my U. So it's just a different magnitude. The direction will be the same, V parallel to U. Now, what's cool about this is that if I can find this lambda right here, that will make it very easy for us. Well, that lambda turns out to just be the dot product between V and U. So this piece right here is my scalar. That's my lambda. Here is my U vector. And that would tell me what V parallel is, which is my projection of V onto U. So what we end up with in the end, projection of V onto U is equal to V parallel. Well, V parallel is just some magnitude of my U vector. And depending upon what vector we're using, that's as long as the magnitude of U is equal to 1. If it's not, you go ahead and take it and divide it by its magnitude to make it so that it does have a magnitude of 1. And this is upon the condition that V is equal to V parallel plus V perpendicular. So that's just the two components, the IJ components. And then V perpendicular is equal to V minus V parallel, which is based upon the components as well. So here's a couple things. First of all, here's some notation for projection of V on U, which I think some people write. So this is what our book does. That's as long as the magnitude of U is equal to 1. So we're just finding this. Remember, this is a scalar. The dot product is a scalar. So that's just multiplied by some vector U. Then if I want to do it a different way, if my magnitude of U is not equal to 1, I just have to go ahead and divide by the magnitude of u for both of those to put it so that the magnitude of whatever I have here, this thing, is going to be 1. So that's two formulas that you can look at. For the projection work, we'll try some of that in class. Now the last piece would be the work. Work is defined to be some force acting on an object through some displacement, and those are all vectors, is given by the dot product of the force times the distance, or displacement, I should say, of whatever happened to whatever we're working with. And so here we have a particle. So suppose that we have some force vector, and its displacement vector can be d equal to 1, 2, 3. Find the work done by this force on moving a particle from the origin to that 1, 2, 3. So when I see work, I'm going to do the dot product of the force times that displacement. Notice again that W is a scalar. It's going to turn out to be a number. I'm using the parenthesis notations. A lot of books will also use these kind of more triangular brackets, but this is just going to be equal to 2 plus 6 plus 12. So that's 18, 20. So the work being done by this force in the direction to move it from the origin to 1, 2, 3 is going to be 20. And we represent that as joules. Some of you have learned this a little bit in physics so far, but that would be the work units that we do have. All right, this is kind of long, I apologize, but we have a lot to do there. I hope you enjoyed this. Thanks for listening to 13.3, and we'll take care of some more questions in class. Have a great day.